I'm going to show you how to make this plot. And this plot is the wave function for a particle in a 2D box. So maybe you've done a 1D box. Now we're going to do a 2D box. And it's a great review of the stuff that we do in the one-dimensional infinite square well. But there's some cool things also in here that aren't in the 1D well. So let's just get started. Number 1. This is my box. I drew this in Python just to kind of get you an idea of what's going on. There's infinite potential walls in one direction. And so the particle can only move in this, I'm going to call it the XY plane. And that box could be anything, right? It could be a square or it could be a rectangle. I'm going to do a generic rectangle case, and then at the end we can change it to whatever we want. So there's my particle right there. And I want to, find the probability, distributions, and all that stuff. Solve this equation. Okay, just a really quick review. In one dimension, this is the one-dimensional infinite square well, the Schrodinger equation. That's just our Schrodinger equation. And we broke that into a space part and a time part, and then we found the time solution, which I'm going to go back over in a second, and then we found a space part. So we're going to do it differently, a little bit different for the two-dimensional. Also, I should point out that I normally would write this on paper. I'm trying something different using pre-made equations. I don't know which one's better. I kind of like writing it better because this takes a lot of time, but I'm just letting you know I'm trying new things for you. Here is the 2D Schrodinger equation. We have this second partial derivative with respect to x, but in 2 dimensions, we're going to have to replace that with this, right? We're going to have the del squared operator, and it takes the partial with respect to x, second partial with respect to x, plus the second partial with respect to y, plus the second partial with respect to z. Now, we don't actually have any z things here, but that's still what it is. And this is in Cartesian coordinates. If you want to use that operator in spherical coordinates, it's not so pretty. If you want to use it in polar or cylindrical coordinates, not so bad, but it's not as nice as Cartesian. Cartesian's just the nicest. So anyway, this means that we get the following Schrodinger equation now. So we've replaced that second partial with respect to x with the del squared operator. That's the only difference. Okay, so how do we solve this problem? Well, and I'm also going to assume that my potential, and we'll use this later, but not really, only partially. My potential, 1, does not depend on time. That is super important. No time dependency in the potential. And then maybe I can separate the x part and the y part. You can't always do that. But if you could have an x potential plus a y potential, that's going to be really awesome. Now let's look at the time dependence part. So let me just say that capital psi, that should be of x, y, and t, is equal to a space part times a time part f of t. And we did this before. If I put that in to my Schrodinger equation, then right here, when I take the partial of psi, capital psi, the lowercase psi doesn't depend on time, so I can pull that out front. And the same thing's true over here. Since the space derivative, there's a time part, doesn't depend on space, it's a constant when I deal with partial derivatives, so I can pull it out front. And then I have both of them right there. Okay. So the trick is to then multiply by 1 over psi f for both sides of the equation. If I do that over here, that psi cancels, but the f doesn't cancel. Over here, the f cancels, but the psi doesn't cancel. So I end up with this equation. Now, what's super important about this equation is that I have right here stuff that only depends on time. There's no space part in there. There's no space variables in there. And right here I have something that only depends on space, x and y. It does not depend on time because my potential is space dependent only. So this part only depends on time. If I change this, then this doesn't change. So that says that this stuff has to be equal to a constant, right? Because otherwise, this would have to change too. And the same thing's true for this. If I change x, then it's equal to this because that does not depend on x. So they both have to be equal to constant. We call that constant e. Okay, so now if I just look at the time part, I have this differential equation. I h bar 1 over f partial of f with respect to t is e. And I can solve that by guessing a function. So what function do I take the derivative of? That I take the derivative of and I get negative I over h bar f, right? I should have put that equation in there, but I didn't. And it's this equation. That's my function for time. And it's exactly the same as the one-dimensional case, right? Because it doesn't have any it doesn't have any space stuff in here. It doesn't matter. So that's important. We put a box around that. I like to put boxes around things that are important. Now let's move on to the space part of the differential equation. So that space part is equal to a constant also, e. And that's wrong. That should just be e. Should I delete that right now? No, it's right. That's right. Because right here. Yeah. So I had that 1 over psi. I multiply both sides by psi, and that's why that's e psi. Okay, sorry about that. Sometimes I confuse even myself. Okay, so that's my space part of the differential equation. Now what I'm going to do is to assume that my psi function has a space part x, capital X. And I'm going to say x, that means capital X. I'm going to say y, that means capital Y. When I say x, that's the variable x. When I say y, that's the variable y. I know it's very confusing when you say it, and that's why it's nice to write this out. And that's one of the reasons why I did this with the presentation, because you can definitely see the difference between capital X and lowercase x. When I write it, it's sloppy. I mean, you could call that function anything. This is what most people call it, though. If I take that function and I put it in for my into my differential equation, I get this. So now I'm going to put this in for psi right there. I'm just looking at this part. If I do that, I get the second partial of this with respect to x plus the second partial of xy with respect to y. Well, here the y doesn't depend on x, so I can pull that out front. Here the x doesn't depend on y, so I can pull that out front. So my second derivative of space, I can write it as this. So going back to the differential equation, now I'm going to put everything in. There's my space derivative right there. And then I have my potential v, it's vx plus vy, and then psi is xy, exy. And then I have that constant right there. So the trick here is to multiply both sides of the equation by 1 over xy. If I do that, these are going to cancel, those are going to cancel, this is going to cancel the x, and this is going to cancel the y. And so I get this equation, negative h bar squared, 1 over x, right, because that y canceled, 1 over y. But now I have a term, this is really nice, I have a term that only depends on x, and here's a term that only depends on y. So we're back into the similar situation that we had before. And then here I have the energy minus the potential, and I can actually write this as the following. I can say there's an x energy minus the x potential plus an e energy minus the e potential. Why would I do that? Well, if this is equal to a something that only depends on x, and this is only dependent on y, and I add them together and I get something that is a constant-ish, and this is not always true, but in this case, if v is 0, then e is a constant. We already know that, right? Then this has to be a constant, that has to be a constant. Otherwise, if I change this and I don't change that, it's not equal to a constant. It's the only way it can work as a constant. So I'm going to call that constant e. I'm going to break it into ex and ey. So e is ex plus ey. And then I put the v's with them just because if you solve the differential equation a different way, it's useful to put it in there. So, okay. So let's look at just the x part of that equation. So if I take this equation and I take the ex minus vx, that is equal to this stuff, right? Just the x part. And then this is just the y part. Even if vx does change with x, still, if I change this x, that could change, right? But it wouldn't change the y part, so that's fine. And then I could take this constant, right, this thing right here, Ey minus Vy, and set that equal to the y part. So I get two one-dimensional differential equations. That's important. Now we're in an infinite square well. So I can say that Vx is 0 and Vy is 0 because that's the solution I'm looking for at the floor of that box, right? The walls have an infinite potential, but in the floor it's 0. And you can do different potentials later, but we're doing the simplest case. So this becomes my one-dimensional infinite square well x equation. So I have negative 2m. No, I have this is my second partial, and then I multiply both. So I'm taking this and setting it equal to ex. And if I just solve for the second partial of x with respect to x, I get this. So this says that I take the derivative of x twice, and I get back the same thing with a negative and a constant. And let's call that constant kx squared, where kx squared is just that stuff right there. Okay, so if that's the case, I know the solution to this differential equation because I can guess it. What functions, when you take the derivative twice, do you get the same thing back? And the answer is, one of the answers is sines plus cosines. Sines and cosines, when you take the derivative of cosine twice, you get the cosine back with a negative. When you take the derivative of sine, the same thing's true. Okay, so this is my solution. I have a constant a out front, I have a constant b out front, and then that kx is this square root of that. Kx is the square root of that. When I take the derivative twice, I get that kx, and I get the same thing. You can check it out if you want to. I didn't put that in there. I want to solve for a and b, if possible, and other things. We did this again with the one-dimensional square well by applying the boundary conditions. So my box has a corner at the origin, and then at the x width is a and the b width is b. I mean the y width is b. So here's my function. We just had that. And I know that at x equals 0, the function has to be 0, right? Because there's no possible way it could be outside of that box. So the wave function has to be 0, so the x part of that function has to be 0. If I put in x equals 0, then I get a cosine of 0, I put the 0k, plus b sine of 0. Well, sine of 0 is 0, so that term's gone. And that leaves me with a, because cosine of 0 is 1, plus 0 is equal to 0. So a is 0, right? So now I have this as my function, x of x, b sine kx. But now, could I find b? Well, I can't. Well, I can, but I can't. Let's apply the other boundary condition at x of a is equal to 0. If I put that in, I get b sine kx a is equal to 0. So, yes, b equals 0 is a solution, but a boring solution. Because if I have a plus and b are both 0, then x is just 0. And what fun is that? That's not fun, right? So let's not do that. Remember that if I let this variable k be a multiple such that the interior of this is a multiple of 2 pi or pi, then I get 0, right? So if kx is nx pi over a, where nx is 1, 2, 3, 4, then this is going to be 0. Same exact thing happened for the one-dimensional infinite square well. Okay. And so we could then go back over here, now that I know this is my conditions for kx. Remember, we set kx squared with this thing, so I can just solve for kx, and I get this, which is kind of cool. So now we have a relationship between this quantum number in x and the x energy. And then, I'm not sure why I put that there. Okay, because it's important. So that's my solution in the x direction. That's my constraint on k, and that's my quantized energy. Remember, this is the same thing that happened in the 1D square well. This boundary condition forces a quantization of energy, right? That's why we have that. Okay. Now let's look at the y equation. It's the same thing, except it's y, and there's a condition about the other boundary is b, not a. So here's my y equation. This is identical, but it's good to go over. Again, solving for the second partial of y with respect to y, I get that. I get a this thing I'm going to call ky is different, right? Because it has to deal with ey. So those are different things. Using the boundary condition for y equals 0. Oh, I don't know. I didn't animate that. That's a thing. Y equals 0. Plug in y equals 0. I get a is equal to 0. Plug in the other condition, y of b is equal to 0. That would mean that b sine, and I'm using b again, and that's a bad idea, but it doesn't really matter. KYB is equal to 0, so there's the part that I want. That means that KY has to be in y, a new quantum number, right? That's a different number. Pi over b, because that's the width in the other direction. And I can use that to solve for the energy, and ny would be also 1, 2, 3, 4. That's the in quantum number. And then I have all those things. Those are the important parts of the y. And now I can put it all together. Here I have the total wave function is my x, my y, and my time. And I have b sine kx. I had another b sine kyy, right? And those are both just a constant, so I pulled them together and I called it just b instead of writing b squared. They would be different terms anyway, but just a constant. It doesn't really matter, it's just a constant. And then there's my time part, e to the negative I, e, which is the total energy, remember, which is ex plus ey, t over h bar. That's your total energy is ex plus ey. And remember, ex depends on the quantum number in x and the space part a, and ey depends on the quantum number in y and the space part b. So they're not the same. And then I have kx, I have ky, and then nx is 1, 2, 3, 4, ny is 1, 2, 3, 4. Okay, but we have one more thing to do, and that's to find the value of b, right? Because you can't do anything if you don't know b. And this is where we get into normalization. So this is my wave function, the whole thing. If I take psi star psi, that's the probability density, and if I integrate over all of the area in this case, then that probability density, the total probability has to be 1, which means you have to find the particle somewhere. So this is a lot like normalization in the 1D square well, except that we're in 2D. So we have to actually integrate over both dimensions. It's a surface area integral. And I put negative infinity to infinity because it's over all space, and that's for both x and y, and I didn't put it there because I don't want to. But we're going to do it for the infinite square well, so we're actually going from x equals 0 to a, y equals 0 to b. And we're going to use nx equals 1, ny equals 1. We're going to normalize it for the lowest energy state, n1, nx equals 1, ny equals 1. So now the nice thing here is I have psi star psi. That's psi star. That's the space part, time part. But it's a complex conjugate. So when I take the complex conjugate of this, I get e to the I et over h bar times e to the negative I et over h bar. And that's going to just be equal to 1. So that's kind of nice. Now I get the following integral. Both of these do have a b term in there, right? So I get b squared, and then I get sine kx times sine kx x. So I get 2 of those, sine squared. I get 2 of these, and then I have dx dy. Now, fortunately, we can break that into pieces, right? I can pull the b squared out front. This integral, I can integrate the x part. I can integrate the y part because there's no crossover terms. And if I do that, here's my equation again. If I just integrate the x part from 0 to a sine squared pi x over a dx. I've done this integral before. I'm not going to do it again. It's a over 2. The average of sine squared is half, and then you have that a term, so you get a over 2. And then do the same thing for the y term. I get b over 2, okay? And then when I put it all together, I get b squared, that was pulled out front, a over 2, b over 2, and I set it equal to 1, and then I can solve for b. So b squared is 4 over ab, take the square root, and there you go. B is 4, square root of 4 over ab, box that. Okay, we're moving right along here, and that's my final solution. Pretty cool, huh? Okay, but now we want to plot it. And this this depends on both x and y, so we're going to have to do some two-dimensional plotting, which is never super fun, but I'm gonna walk you through this as I would a normal person. Okay, so let's jump up here to, I'm using Jupyter notebooks. I'm using real Python because although I love Web v Python, it doesn't really do 2D plotting or 3D plotting. I guess I call it 3D plotting because I'm plotting x versus y and then psi. So I'm going to use this. There are some tricks you can do, but let's just use this. Okay. And if you're not familiar, I'm going to make a tutorial about plotting 3D plots in Python, and I'll be a separate. So I'm going to go through things kind of fast. And then if you want to watch the other video, watch the other video. So of course I need to import my stuff. Import numpy as mp. Import matplot, plot, lib.py, plot as plt. And then I like to run that to make sure things are running and importing correctly, and what the heck is taking so long. There it goes. Okay. Now I'm doing a numerical plot, so I need numbers. Let's use simple numbers. H bar is equal to 1, M is equal to 1, A is equal to 1. I'm going to pick B is 1.5, and we can change that. And then my B, my normalization constant, is NP times the square. NP means I'm using the square root from the numpy function. Square root of 4 divided by A times B. I need that. Now what I'm going to do, I want to define a function to calculate the energy, a function to calculate I guess I could do each one. I'm going to do each one individually. I don't have to do that, but I am. So let's call def EX, and I'm going to give it NXT, which is my X, my X quantum number in X. And I put the T there for temporary, just so I have a different variable inside of my function than outside of my function. And again, remember, I'm not a programmer. I'm a physicist. And I don't like to do things that are super programmy because I want to get to the physics. And Python is a tool. And I want to use that tool as simple as possible. Not the most elegant way, because that's a little intimidating for me. Okay, so I'm just your normal physics guy doing Python. So if I do things wrong or not the best way, I'm trying to show you can do it your own way. Thumbs up for that. Okay, so this is I'm just going to return my my energy, which is nxt squared times pi squared, which is in numpy, pi squared times h bar divided by 2 times m times a squared. That's what I'm going to return. And then I'm going to do the same thing for y. Let's just copy that. Y, and then it's going to change this to y. And you got to say it out loud when you do that. Y, change this to y. You got to emphasize that too, right? Or it won't work. Trust me. Try it, and it doesn't work. I'm going to change this to b. B, see? Now I can also calculate the total energy. E, I'm going to give it E as a function of nxt in yt, and it's just going to return ex nxt plus ey in yt. So I'm going to use those other functions to calculate that. And let's just try that. Let's just print. I'm going to show you something. Oh, what happened? I know what happened. I missed a parenthesis somewhere. Okay. That is fine. See, because if I do this, okay, no, I guess it didn't. Let's just print. Let's say print E11, 1, 1. So it's n is 1, nx is 1, ny is 1. Let's see if that works. See, it didn't work. EY is not defined. Aha! See, what did I say? I said, when you change things, you have to emphasize EY. Now it worked. Okay. Now, let's pull this up a little bit so you can see. I don't need all that stuff. EY right there. Okay. I do want to show you something. This is the best example of degeneracy. And we don't get this in the 1D square well. But now that we have two quantum numbers, you can actually get energies different ways. So let me put this B at 1. So they're both at 1. And I'm going to rerun that. So there's my energy level for 1, 1. Cool. Now I'm going to print, watch this, print E1, 2, print E2, 1. Those are the same. Oh, you can't see that. Pull this up. There. Those are the same energies. So this is degeneracy in that we have two different versions of quantum numbers, but they give the same energy. It's kind of a big deal in other situations, and this is the simplest situation you can see it. Now, but look, if I change B to 1.5, they're not the same. We do not have degeneracy. So degeneracy needs two quantum numbers and some type of symmetry. You can get it to work with like A is 1 and B is 2. There is some degeneracy in there, but it's not the same. Okay, that's important. I'm pointing that out. Now let's move on. Okay, now we need to do. We're gonna make a three-dimensional plot. I have X is changing and Y is changing, so I'm gonna need to use a mesh grid. So if you haven't done mesh grids in Python, that's fine. I'm gonna make another video on this. Let's go ahead and do this. How many points do I want? 100. I can change that. Now I'm gonna make my X variables. So X is np.linspace. I have a Python cheat sheet, a NumPy cheat sheet video too that you might want to find useful. I will try to remember to link that down below, but sometimes I forget. If you type comments down below with your fingers, I usually reply. Unless it's like 5 years from now, then I don't always reply because I'm like, I don't remember what I did. So it's kind of, I'd have to rewatch the video, which I may reply anyway. So I want this to go from 0 to A, and I want n+1 intervals. Numbers, right? And that will give me n intervals. Okay, that's a good trick. And let's do Y is np.linspace. And you could do a range, 0 to B n+1. So it's going to be the same number each way. It doesn't really matter. Now I need to make my mesh grid. Let's put this at 10, just so we can print this. I shouldn't do this because I'm going to make this in my other video. I'm going to print X. There's my X. Now I can make a mesh grid, right? Because I want to have all my possible X values matched up with all my possible Y values in like a grid of graph paper. I'm going to do that with capital X and capital Y equals np.meshGrid, and I'm going to print that out, don't worry, of X and Y. So this is going to make two new variables, X, which is all the X values, and Y, which is all the Y values. And let's go ahead and print X and Y. Capital X. Some people, you could technically use lowercase. You can make it that way, but I like to do it this way. So here's my X values. You'll see here that I have 0 to 1 and 0, 0, 0. So I have all my possible permutations of X. And then down here I have all my possible permutations of Y, but they're separate, right? So if I look at right here, I get 0 and 0, 0 match that up. 0.1 matches up with this, 0. 0.2 matches up 0. So I get all the combinations by having these two things rotated like that. It's kind of awesome. Let's not print it. Let's put it at 100. And then let's run that. What do I need to run it? Okay, now I'm going to make my psi function. And it's going to be a function of these two. They're kind of like arrays, but they're two-dimensional arrays. It's really kind of awesome. Okay, so let's make a function def psi. I should call it capital psi. No, I'm going to call it psi. I'm not putting the time in there, so it's lowercase psi. Psi, and I'm just going to pass it the x nx and the ny. So nxt, nyt. Everything else I'm going to use is global. Let's just return. I'm going to type it all out. It's going to be equal to b times np.sin nxt times np.pi np.pi times x over a, right? That's my sine function. It's sine nx pi x over a. But you notice I'm using the capital X, so I'm getting all of these variables. It's kind of awesome. And then I'm going to multiply that. Oh no, multiply that times np.sine ny. What the heck? What did I do? I hit a button. In yt times np.pi times y over b. And that's it. Yep. Okay. So let's just run that. Nothing happened. That's good. We didn't get an error. Now we're going to plot it. Okay. And I'm going to make that simplest, dumbest plot possible. So I'm going to use, in plotting in Python, and I'm going to make another video about this. In Python, the simplest three-dimensional plot you can make is the contour F, which is a filled contour plot. If you try to make the 3D plots, it's a little bit trickier, but the contour plots, they're fine. Okay, so let's do a contour plot. I'm going to plot X, Y, and psi, and let's just pick the quantum levels 3 and 2. I'm just picking plt contour F. If you can do contour without the F2, I'll show you that. X, I need to give my X variables, my Y variables, and my Z variables, which is going to be the function psi, and I'm using 3, 2. And that's it. Let's just run that. There you go. Did it. Okay. I could do 1, 1. And you'll notice it's just like one thing, which is what you would expect. You can change this to whatever you want. I could do 4, 4, 1. Oops. Stay on page. I don't know why I keep on doing that. Like that. Okay. Cool, cool. Now, one of the things, this looks a little Art Deco-ish, which I kind of like, but we can change the levels of contours. So just levels equals 20, and it looks a little bit better. You can put that as high or as low as you want. I like 20. Let's do 4, 3, just for fun. And there you go. There's my. That's not the probability density. That's the wave function. So the blue, the darks are down, the yellows are up. If you want to see the levels, you actually can do that. PLT dot color bar. Is that what it is? Color bar. Yeah. And you can see that gives you the numerical values for the different colors. And you can do a whole bunch of other options there too. But that's what you wanted. Now I'll just show you, if you take out the F, it works too. The color bar does not work with that. And now you get these kind of, which is actually contour plot. I like it, the filled, but you got to be you. And then you can run this to your heart's delight. You can change all your variables. All good to go. Whew, okay, so that's the 2D infinite square well. It's kind of cool. It's a great review of the 1D square well. And like I said, other stuff, Python. Hopefully I'll put the links down below. But you know me. Okay, that's it. I'll see you later.